Good afternoon, everybody. Today we're going to talk about problem number 3 of the IOI 2022, the radio tower problem. The problem is like this. You have N towers, each one with a height of h of I. So two towers can communicate to each other if between two towers there is another tower in between, right? And then for a given interference value, the height of the tower I and j are at the most of this tower in between in the middle minus that. So basically, you have a between I and j, and you have a peak, which is at least this height of delta. So we want to list some radio towers that are communicating with each other. So the question is, between every range between left and right, with this interference value of d, what's the maximum number of towers we can list? Okay, so here is an example like this, right? So this and this tower, let's say delta is 10. So between this and this, there is a peak, which is higher than any of those by at least 10. And there's a peak here, so this and this can communicate. So this and this can communicate. And this and this can also communicate because either of this tower has a height of more than that. So how do I look at this problem? So if I have a tower like this, so let's say I have a delta, right? So on the left-hand side, let's find the tower that is the first tower on the left-hand side. And let's say this is tower I. On the left-hand side, where its height, right, is bigger than height of I plus delta, higher than equal. So this is my left of I. So on the same token, I have my right of I. The height of right of I is also more than this. So to simplify the drawing, so I'm going to say for each of the I, tower I will have left of I and I have right of I, which is to the left and to the right, which that is the closest to I, and the height of that is at least sigma. So for each one of them, I can define this left and the right. So then if I have two towers, okay, tower I and tower J. So each of them I have this like fork-like structure, right? So the first thing I would argue is if I and J can communicate with each other, that means those two intervals are not, they cannot intersect each other. So it will be nothing like this. Oops. So this is my I and this is my J. There'll be nothing like this, right? If it's like this, then they can still communicate. So then this one, it means this one should also be higher than this by at least delta. But we said this one is already the first one on the right that is higher than this by delta, so those two conflict, right? So my first observation, so the only way that could happen is they will be isolated like this, or they would be like this, one overlap each other. Well, let's say this is my I, and that'll be my J. Okay. So so that's the first one. And actually, if you do this, right, so this one we said it's not going to happen, right? So this one, by the same reason, we also can derive it's not going to happen, right? So if they can communicate, the only way they can communicate is this right hand I and the left hand J have this relationship. Basically, right hand I has to be less than equal left hand J. That's the only way it can happen, right? So those two cannot happen. So that's the first thing. Then the other thing is, so again, for I and J, if right of J is less than left than J, let's say if I have a condition, I'm not saying that they are necessarily communicate. If I have a condition of right of J, I mean left of J is less than right of J, then in this case is this thing has to be at least here. Okay, so the same thing, right? So because this is the first thing that is more than this by I, right? So that means this is more than this by I, and this is also more than this, sorry, more than this by delta. This is also more than this by delta, right? So it has, so that clearly means it has to be out here. Okay, so it's left and I and then left and J. So it has to be overlapped out there. Okay. So is that clear to everybody? So now we have this. Then if I have anything like overlap like this, right? And J, if this relationship works, okay, I chose the other way around. If this relationship works, okay, so it works for something like delta prime for one value. For everything that increase, then this relationship will still works, right? Because it will only when you increase this thing will only go out, right? Equivalent to this thing will only go out. So this containing relationship, if it meet with a certain delta, it will all meet with this thing above it. Okay, so now once we have all those forks defined, clearly the problem we're trying to solve is we're trying to find how many non-overlap forks, right? So in this range, left to right, how many overlap forks we have? That's the only question, right? So basically, that's a question. Okay. So we basically can do D from this sigma from 1 to, let's see, what was the biggest value of D? D is, I remember, it's 1 in 9. Yeah, 1 in 9, right? 10 to the power of 9. Okay, so I can scan D, delta, or H, whatever you call it. I can scan this, right? And if it's offline, if this query was offline, I can just pre-sort it and starting from D from the lowest, the query for the D from the lowest. And every time I update, right? Every time I update, I will increase, right? So when I increase, I figure out which two of those will overlap. Remember, we said if they communicate, if they can communicate, they will not overlap, right? So basically they will merge, right? Eventually they will merge, okay? And only one of them will exist, right? So then I can do this and I can record all of those. But this is an online thing. If it's an online thing, we need to record all those valid, those forks. We need to record all those, right, unique forks. We need to record all those unique forks. How do I do that? So I can use, remember, we can use the persistent data structure, right? Persistent data structure is the one that allow you to keep all the historical ones, right? Without an increasing, significant increase in the memory, right? So remember when we talk about the segment tree, right? So if you have a segment tree like this, the next time you update, if this side is not changed, you just point to the same thing and only update this side, right? So persistent data structure. So we can use persistent data structure to keep all the unique forks when we scan the sigma, the delta from low to high. Once we do that, then once we keep that, then every time when we look at the range, left to right, we just need to count. For that data, we just need to count at that condition how many unique forks exist in that within there, right? The only thing you need to care for is for the first one and the last one. You need to check if it's valid, right? Because this left side, for example, if you have this, then you may put another one here, right? Or this side, you could put another tower here, right? So then you can basically search for it. It's basically a divide and conquer, right? If there's between left and right, there's no effective, if there's no effective fork, right? So if there's no effective fork, then you find in this range, you find the biggest, right? Biggest tower. Then you pick one tower on the left and one tower on the right, right? So that's you build it. If yes, there is an effective fork, then find then on the first one, for the first one, right? So for example, Um, then for this one, right? For this edge, then you find, can you do that? Then yeah, then here's a one, then there's um, then you find that way, right? So you find this one, and then here you find whether you can do this one, right? Then you count how many you see. So what is the complexity of this thing? Um, you would think the complexity all come from you update this fork, right? As I said, every time I need to update this fork and count the merge, there is Q of them, and so there are basically 10 to the power of 9 of them, and basically the Q of them, right? Is each time I need to scan from here to here, does that mean I have O of NQ complexity? Actually, then that doesn't work. So, but if you think about it, it's actually not enough NQ complexity. So if you think about this way, the most it comes from how many times you need to update the fork, right? So let's say I have a tower just like this. Every tower I increase by one. Okay. So the first time the the left-hand side tower is always here, right? So left of I is always here. Okay. So the right eye, when delta is one, it's always the one next to it, right? So it's n of them. Then when you do two, then you merge this and this, right? So then you merge this to this. So distance of two, right? So it's n divided by two. So then the next time you merge, okay? So the next time you say my delta is three, okay? The maximum you would do is like this. Then I have three of them, okay? So n of three. So what you would have is n times 1 plus 1 over 2 plus 1 over 3 plus, right? So what is sum of this? This is, so if we do sum of 1 plus 1 over 2 plus 1 over 3 plus 1 over n, okay? So it is the rough estimate of this is log n. Okay, so this is basically if you want to understand more of this, is the harmonic number, right? So the harmonic number, which is this, the upper limit of this is log n plus one. So the upper limit is log m plus one. So that's your upper limit. Okay. So if you want to understand more, just read this more. Okay. So you have it in Stack Exchange. So the way to prove it is this is roughly equal this integral. Okay. So then the complexity is O of m plus q log n. So that's your complexity. So that's good enough. Okay. So let's come back to look at the problem. So the way to solve this problem is to define all those forks and figure out what you basically, the problem is equivalent to count number of unique forks. Right? Forks, those forks will, if two towers will communicate to each other, those two forks will not overlap, right? Will not intersect. So then we need to count those unique forks. The way to count those unique forks is basically expand it. When delta increase, expand and until they merge. And to keep all those records, then you use a persistent structure to keep those records. Once you have those, it's just basically a simple query of the of that particular tree, right? As that D. So that and the complexity is n plus q log n because of the harmonic number. So that's the question that's the answer to this week's question. So next week we will work on problem number 4. Okay. Have a good weekend and I'll see you next week.